Today we are learning mean value theorem. It is the last of 3 value theorems. And the first value theorem that we have already learned is the extreme value theorem. Extreme value theorem requires your function to be continuous on the closed interval a to b. And if you remember, the extreme value theorem tells you that if this happens, you are guaranteed that there is an absolute maximum and an absolute minimum. And that's extreme value theorem. Then we got intermediate value theorem. Intermediate value theorem required also for f of x to be continuous on the closed interval from a to b. And do you remember a little bit of what intermediate value theorem said? It said if you have some number that is between the y values, then you are guaranteed that there will be at least one x coordinate c. That c is in the open interval from a to b, not at the endpoints, for which its function value will be that number. Now, the mean value theorem begins as both of these begin, with the need for continuity over a closed interval. It adds to that a need for differentiability over an open interval. And let me emphasize what a picture will look like if you have, I'm just going to draw like right here. So what I'm trying to draw for you is the idea of you have x equals a and x equals b. You do not have to be differentiable at the endpoints, but do you see that if those are just sharp turns, that you have a nice smooth continuous graph between two endpoints? So differentiability is not needed at endpoints. Most of the time we're going to have it, but it's not required. You're also going to find that mean value theorem has more similar wording to the intermediate value theorem than to the extreme value theorem. When you are in the middle of the AP test and you notice that you have a value theorem problem, most likely it's either intermediate or mean, and you have to figure out which of the two it is. And I'm going to talk about that after we learn what mean value theorem is. So here we go with what is mean value theorem. We're going to start off with something called Rolle's theorem. You don't have to be familiar with Rolle's theorem like the name, but it kind of puts a little intermediary before we hit mean value theorem. Mean value theorem and Rolle's theorem both have these first two hypotheses. We are required to have continuity on the closed interval and differentiability on the open interval. Rolle's theorem says if your two y values at your endpoints are equal, what is this? If you drew a line between f of a and f of b on the graph itself, do you see that you would have a horizontal line? Well, you're guaranteed that you're going to have a horizontal slope somewhere between a and b, at least once. And then we have these pictures to show that it could be that every point in between a and b is the zero slope. It could happen just once. It could happen more than once. But you are guaranteed that it will happen at least once if you are working with something that is differentiable between the endpoints. And I like to look at this as this helps you to see that that differentiability is a continuity idea about slope. Slope must be continuous. I cannot go from this positive slope to this negative slope without hitting every single slope in between. And 0 happens to be one of them. So, to go from Rolle's theorem to mean value theorem, we go away from the idea that f of a has to be equal to f of b. And what we do is we look at the slope between the endpoints. So if you look at your two endpoints at A and B and just draw a straight line, that is your slope between the endpoints. Sometimes it's called the average slope over the interval AB. And you are being told that your derivative must match that slope in between at least once if you are genuinely continuous and differentiable. Let's take a look at a picture. Have you had enough time to write that down? Because that's actually a very, very, very important thing to write down. Let me leave it there for a moment. The equivalently, you don't necessarily need. All they're doing for equivalently is changing around the equation. It's the same equation either way. Yep. So let me give you a minute to write that down. Okay. And I'm going to say that that is in your textbook. It looks like the majority of you have had enough time to write it down, but I know not all of you have. You can go back and read this and finish writing it. Here is a picture example showing you that the mean value theorem. The blue lines are showing you the slope between endpoints. And what it's showing you is that you have to have a parallel tangent line at least once somewhere between those two endpoints. Not at the endpoints, but between them. And now let's do an example. We're going to specifically deal with this function over the closed interval 0 to 2. When you are working a mean value theorem problem, it is important for you to state that you are dealing with continuous and differentiable. So again, if you have to explain on a free response mean value theorem, which happens a lot, you need to make sure that you clarify you're dealing with a function continuous on the closed interval and differentiable on the open interval. Then you need to find the average slope. Or slope between the endpoints. To do this, I need to plug 2 into my function, so that's going to give me 6. When I put 0 in, I get 0. And I have a value of 3. 3 is my average slope, my slope between endpoints. And I need to be able to show that the derivative of this function has to equal 3 and solve for what makes it equal to 3. So average slope and then derivative. And once you get that, then you must set the two of them equal. Now, in solving for x, I am getting positive and negative 2 over root 3. For this problem, what is it that I was guaranteed by the mean value theorem to happen? What exactly was I guaranteed was going to happen? Oh, yeah. That I'm looking at actually the positive of 2 over root 3, not the negative, right? Because you're guaranteed that C is between A and B. And in this case, A and B are 0 and 2. And then double check, is 2 divided by root 3? Actually, I don't think we have to think too hard about that. 2 divided by root 3, definitely between 0 and 2. So that is my C number. The C that is guaranteed by the mean value theorem. Excellent. Then I decided to show you the lovely picture that the textbook had of the problem. Pretty. Parallel. Parallel. Pretty. And I can see some of you are still writing. And then I've got one more example with mean value theorem. And you can also watch this video later if you missed something there, but this is directly out of your textbook as well. Okay, I've seen problems like this in multiple choice on AP exams. They'll ask things like, which of the following could f of 2 be? So take a good look at it. It gives you 1 point of the function. You're told that the derivative is less than or equal to 5 for all values of x. And if an AP exam said which of the following could be f of 2, only one of those answers is going to be possible based on the information. I find that with these problems, I like to draw what I'm looking at. But for some of you, you may go about it in a different way, and that's perfectly fine. Do what logically makes sense to you with this problem. For me, I prefer to draw it out and look at, okay, I've got a particular point here, and I'm being told that the slope is less than or equal to 5, so it can't be any more than 5. And I'm looking at what are my possibilities for f of 2 if I cannot be any steeper than 5 at any given time. So I want to give you a moment to think, how would you do this? And if we were able to go around, we would get a variety of ideas on how you view doing this problem. Basically, if I'm going to go 2 units to the right, then I can at the most go up 10. So 10 above this number. Trying to get my pen to work. Oh, well, you work when you want to. But... So basically, f of 2 has to be 7 or smaller. How large can f of 2 get? It can get to being 7 at the most. All right. In your homework, I have some AP problems for you, as well as some bookwork problems. And now I'm going to go back over to optimization problems. And I want to finish going over the examples that the textbook gives. And then I want to repeat that we've got 3 days after this where I can go over homework problems or various questions that you've run into. This example is similar to one of the homework problems you had over the weekend. It's saying, let me get my cursor out of the way. Okay. It wants you to find a point on the parabola that is closest to the point 1, 4. So you can see the point 1, 4. And then with a point on the parabola, it could be any of these points. I mean, so it's obvious it's not these over here, but we need to use calculus. The point is just practicing what calculus can do so that when more sciencey problems show up your way, you know what steps to take. This is a very mathy math problem where the application is pure math. It's not really something that you would necessarily need to solve. But this allows us to go through the process of optimization without learning something in science. So what exactly are we trying to optimize if we want to find a point on the parabola closest to 1, 4? What are we optimizing? And I'm looking at chat. Distance. We are optimizing distance between the point 1, 4 and some point on this parabola. Now the example gave us this generic point and said, hey, it's x comma y, to kind of help you get started. So what is a formula for distance between 2 points? Do you recall a formula for distance between 2 points? Now, if nothing is coming to mind, which I know is happening for some of you, let me remind you, let's say I have some x1, y1 and x2, y2. If you don't remember the formula, what you want to remember is the distance between 2 points is a hypotenuse on a right triangle. If you can get that picture in your head, the formula will come to you faster. The horizontal distance between your 2 points is your change in x. The vertical distance between the 2 points is your change in y. So you're doing a Pythagorean theorem on change in x and change in y. And you don't want to just memorize this formula outright, I want you to look at it and actually see Pythagorean theorem. See that leg squared plus leg squared. And then think about the fact that your change in x and change in y are perpendicular to each other, so it makes sense that they would be the legs of a right triangle. All right. Now, we have a generic point xy and a specific point 1, 4. When you have an optimization problem and you're dealing with single variable calculus, you need to get an equation for what you're optimizing in terms of one variable. Right now you have two variables that distance is in terms of. And sometimes you want to ask yourself, well, what is the relationship that x and y have that's so important? And that might get you to realizing, oh yeah, hey, look up there. Whoop, whoop. They have to be on that parabola, and that forces a relationship between them. Your goal now is either isolate x or isolate y and plug it in to this formula. And take a moment to just think, what's going to make my algebra easier or harder? If you look at it for a bit, you should see that isolating y may not be the better way to go here. If you isolate y, you're going to have a square root, subtraction next to it, and then a squared that you can't just distribute over subtraction. So it's going to be very painful if you go that direction. That means we're going to take this and isolate our x in terms of y and plug it in to the x. And I need to still see it. And now we've reached that moment where we have an equation for what we're trying to optimize in terms of only one variable. I could look at this graph on a graphing calculator, where the y on the graphing calculator is representing the distance, and awkwardly the x is representing the y coordinate. But it's important that you see that you're dealing with this being a function with respect to a variable. And if I want to optimize it, one thing I've got to look for is a relative minimum maximum. And when I have a relative minimum maximum, this graph is going to have a zero slope. And that's why I need to find the derivative and solve for what makes it equal to 0. So I'm going to go ahead and take the derivative as it is. And as I go along, I'm going to talk to you a little bit about a shortcut that can only be taken in this situation. And I advise you to never use shortcuts unless you actually understand why they work, because then you might apply them to areas where they don't work. All right, here we go. We've got a big giant square root. So 1/2 blah to the negative 1/2 will end up giving me a square root in the denominator with a 2. And I'm going to change colors so that we can see the difference. In the middle of the chain rule now, I'm taking the derivative of what's under that square root. So I start off with parentheses squared. So I have 2 bleh. Chain rule says I plug in the function, multiply by its derivative, and then I have an addition sign. And next parentheses squared, I take the derivative. And there we go. Now I'm going to explain to you about the shortcut that the textbook begins to talk about here. Look at this denominator. Why did you multiply by y? Right. Oh, I multiplied by y right here because that was the derivative of this, because it was 1/2 times 2y. That silly divided by 2 is annoying. So what I'm going to do is I'm going to rewrite this as 1/2 y squared. And then when I take the derivative, I've got the constant multiple times 2y. Yeah. So this square root in the denominator is something we actually started with. That square root is the distance between our 2 points. When I'm looking at critical numbers, I'm looking at what makes the derivative 0 or undefined. The undefined part is looking at that denominator being equal to 0. That denominator is actually just the distance between the 2 points times 2. When will the distance between the 2 points be equal to 0? If you are looking at a point on that parabola, it'll never be 0. So our denominator is actually not going to create any critical numbers for us. That means we can focus on just the numerator, which means that's really focused on ignoring the square root completely. So the textbook talks about optimization happening at d squared in the same place where it happens for d. I want to point out to you what in the derivative formula is important to be aware of, because I really advise you to not use shortcuts. But if you're familiar with this problem, you should be able to relatively quickly see that this piece is not part of what's going to make the difference here, and that I can focus on just that numerator. What I want is to not waste time with my denominator. I don't want to waste time trying to solve for that equation equal to 0. Because can you picture yourself doing that, or someone you know? Because I can definitely picture doing that. Just getting into the moment and leave no stone unturned in algebra. So just be aware of that. In the book problem that you guys had over the weekend for homework, that one, the point was actually on the ellipse itself, but you were maximizing distance. So the thing that made its denominator 0 was actually what minimized your distance to be 0 itself. basically, don't just completely ignore pieces of a function. The distance formula is a very special case where this happens. So if you do read problems where they just flat out ignore it, I want to tell you, don't completely ignore it, consider it, and then realize what you need to do. So this numerator, I need to solve for what makes it 0. I'm going to distribute my multiplication of 2. That will give me y squared minus 2 times another y. And then distribute this 2. And I want to know what makes it equal to 0. Aw, it's like the textbook made it happen super nice for us. So, what number makes y cubed equal 8? All right. Now, this is where the optimization occurs. We can take the time to analyze as far as the y coordinate of the point on this parabola. It can be anything. The domain of the distance function for the y coordinate is all real numbers. You have one critical number. If you need to justify that that is your absolute minimum, you just need to express that when y is less than 2, the rate of change of distance is, and then put positive or negative. And when y is greater than 2, it's the other way around. And let's see, if I go back, I can play with it and figure it out, but it should be coming out as when y is less than 2, the rate of change is negative, and then after 2, it is positive. In order for this to be an absolute minimum justification, you have to include an explanation of the full domain. This justifies that the absolute minimum occurs when the y coordinate is 2. From there, you can go back and finish the problem. And the point would be some x coordinate comma 2. And if oh boy, that's just 2, 2. Whoever came up with the 2, 2, it's adorable. I like tutus. They're cute. And they make watching ballet more enjoyable. Okay, moving along. Okay, I'm going to tell you what this problem is saying because it's very wordy. What it's saying is, you've got a person sitting at point A. They want to get to point B, but they want to get there as fast as they can. So they're trying to figure out, by rowing their boat and running, what is the optimal point that they can row to minimize their time. You know, thinking about it, if you're like doing some triathlon, that could be a very important calculation prior to the race. So, you know, we could see some real world with this, maybe stretching it there. Now, what you are told in this problem is, and I've got to admit, this textbook does have, this textbook that you're using is older than you are. It has yet to try to balance the genders a little in its word problems. And it's always he is doing stuff. So I'm going to say she. She is going to be rowing at 6 kilometers per hour and then running at 8 kilometers per hour. Anytime you have an optimization word problem, you're trying to figure out, what am I optimizing? In this situation, you're optimizing time. You're optimizing the sum of 2 times. It's going to take you a certain amount of time to go from point A to point D. And that's going to be based on rowing. Then it's going to take you a certain amount of time to go from point D to point B while you are running. All of you are familiar with the formula that distance is equal to rate times time. And I'm going to put rate as technically speed. A lot of times textbooks will use the letter V for speed, even though we think of V as velocity. But I'm going to use V right now as speed. So what is an equation for time? Time is distance divided by speed. So I've got my rowing time, which is going to be the distance that it takes to go from point A to point D, that distance, divided by the speed, which is 6 kilometers per hour. For running, its time, I need to be looking at, I'm going to put a sub D1 with the time 1 and a sub D2 for the time 2. I need to know this distance, and I'm going to divide that by the speed of running, 8 kilometers per hour. And now the hard part is, I've got to get a formula for the 2 distances. I've got this distance, and I've got this distance. I'm going to erase so that we can see the picture a little bit better. I'm also pausing to give you some time to think about it. So if you take a look at A to D, you know that this river is exactly 3 kilometers wide. How is that going to help you with finding the distance A to D? Do you see any math pictures coming in? Pythagorean theorem. So this is 3. I've got a right angle here. And I need a formula for this distance. Additionally, I need a formula for this distance. And I do know the distance 8 between C and B. Do you see a good place to throw a variable? A variable that we can use in a formula for distance 1 and in a formula for distance 2. And realize that our issue is trying to come up with a formula for very different places, different ways of finding distance, but somehow based on only one variable. Is there something where, like a length that connects the two, that they have in common? Is there something that they both have in common? Well, 3, 4, 5 triangle force you into a very specific triangle, but the x plus y equals 8 is definitely something that's on the right track. Do you see a particular line segment that would make a good variable here? A particular line segment, yeah. And, you know, this isn't something that's obvious. You don't have enough time right now while you're in the middle of a class, and I only have an hour to get through a bunch of problems with you. You don't have enough time to really sit and process this on your own and take the time to come up with it. This is not obvious. So don't feel bad if you don't see that. In fact, I'd be surprised if you did. So this length right here, we'll put variable x on there. And that means that my formula for distance 1 is the square root of 9 plus x squared using Pythagorean theorem. 3 squared plus x squared. That distance will be divided by 6, and that will tell me how long it takes to row. Then for distance 2, what's the formula for distance 2? Oh, the 9 comes from 3 squared. Good. 8 minus x is the formula for this distance because we know this is 8 kilometers for sure, and we're taking away whatever that x distance is. So this d2 is 8 minus x. And to get the time for running, we divide it by 8. And we need to add the 2 times together, and that is what we're trying to optimize. So I'm going to say t equals, and we have a formula in terms of one variable. No one, okay, not no one, but people generally are not going to come up with this quickly. I've looked at this problem already. That's why I knew where it was heading. It isn't a magic trick of being able to magically see this quickly. It takes time. Time. Okay. Here we go. If I want to optimize this, that means I need to find where the derivative is 0. And it's really important that you understand why we're doing that. We're looking at time as basically the y value of a function, and this x is the input of that function, which we usually see horizontally. If we want time to be minimum, then if I'm looking at a graph of time with respect to that distance, I want to find a minimum time. And that minimum time is going to happen when the derivative is equal to 0. So does everyone see why we're taking the derivative and setting it equal to 0? So let's go. And I'm just going to roll this out a little bit quickly so we can get through a next problem in 10 minutes. So 1/6 times 1/2 blah to the negative 1/2 will end up being this times the derivative of the inside function, and then plus, and the derivative of this is going to wind up being just plain old negative 1/8. And I need to get a common denominator going. Let's see what I can do to save my breath a little bit, though. Let's save that breath. Then I need to figure out exactly what's going to get this least common denominator, because I really don't want more numbers than I need. So as far as 6 and 8 go, their least common multiple is going to be 24. And then I've also got to bring in that lovely square root. And now I've got a common denominator. I'm trying to solve for what makes it equal to 0. And hopefully you can see that that common denominator will never equal 0. So I'm going to focus on the numerator, which is 4x minus 3 times the square root. And sometimes when you're solving equations without a calculator, you don't know where it's necessarily going. You play with it, and then all of a sudden you go, ah! And do you see what we can do right here that's going to be just yes? No more square roots. Square both sides. And let's see, if I subtract the 9 from the 16, I get, I thought this, hold on a second. Did I mess something up? Because I remember a different number last period. Have I messed anything up? No. Okay. Maybe I'm just remembering wrong because I do that. Okay, so I have 16 minus 9 gives me 7. That's right, right? Yes. I'm starting to think I may have done my arithmetic wrong in the other class. So anyway, continuing on, I have a very lovely number. And that is the distance 9 divided by root 7 is this distance that I need to have between C and D for where I try to land my rowboat. So if you're running a triathlon, that matters. Got to minimize that time. Otherwise, you might want to just estimate and row. So one more example, and we have 6 minutes, so we can do this. We need to find the area of the largest rectangle that can be inscribed in a semicircle of radius r, as you see in the diagram. I understand that this may not be something that matters too much, but we are solving math problems to see how to do the application so that when we learn the science in a science class, we understand how to use an application in the science class, hopefully. All right, now, what are we optimizing? We are optimizing area of this rectangle here. They kindly showed us that 2x is the length across if x is the x coordinate of that point, and that y is the height of this rectangle if y is the y coordinate of this point. And if this point is in quadrant 1, then I can use positive x and positive y as distances. And that means the area is 2x multiplied by y. With optimization, your goal is to get an equation for what you're optimizing in terms of only one variable. And so we need some relationship between x and y. Keep in mind that we are being expected to use the radius r as an unknown constant, so we're just going to have to deal with it. Does anyone see a formula of how x and y relate to each other? When I get this done, I will try to address the questions I see in chat and help you see that. I'm trying to draw a straight line. So can you think of any formula that relates the x and the y together? Pythagorean theorem. If I use Pythagorean theorem, then I'm looking at x squared plus y squared equals r squared. But you could have also thought it's a semicircle centered at the origin. What's the equation of a circle centered at the origin? X squared plus y squared equals radius squared. Remember? And make sure that you know your distance formula and your equation of a circle both originate with Pythagorean theorem. When you're dealing with a circle, you have a particular hypotenuse distance at all times. So you have leg squared plus leg squared equals that constant distance squared. Now, unfortunately, I'm going to have to go into square root land and solve for y. And I'm only going to need the positive square root because y is a positive quantity. based on how this is made. And I've got to deal with R as an unknown constant. With R being an unknown constant, I have area in terms of only one variable. That means it's time to take the derivative, set it equal to 0, and solve. So I'm going to go into the product rule. And if you must go for lunch, you are allowed to go. I'm going to keep recording. Did the question in chat get answered? If you still need some help on that, stick around and I'll help you in just a moment. I'll make this quick. I've got this x, I've got this negative 2x, so I've got negative 2x squared over a square root of r squared minus x squared. And then over here, plus 2. Common denominator. And then what I'm going to do is just write the numerator alone. The numerator is negative 2x squared plus 2 times the quantity r squared minus x squared when I multiply these roots together. And I want to solve for what makes it equal to 0. So I have negative 2x squared and another negative 2x squared making negative 4x squared plus a 2r squared. And I need to solve for x. So I'm going to have, that's going to wind up being, let me think, and a 1/2 r squared. Now, plus or minus, x is only being positive since we're dealing with quadrant 1, so it's definitely positive. And I wind up getting the radius divided by root 2. Which is actually really, really interesting. Oh, I tried to do the algebra too quickly. So from right here, I have 2r squared equals 4x squared. Then I divided by 4 to give me the r squared over 2. I think I'm losing you a little bit in the algebra. Let me say something real quick, and then I'm going to stop recording, and then I'll figure out what your questions are, because this is actually really interesting. If I'm getting r divided by root 2, what angle does that make this? Yes. That makes this a 45-degree angle. And if you think about it a little bit, you might go, really? I could have just used geometry. And the answer is yes, yes. Geometry would have been far easier to use. And what the course is trying to do for you is help you to see how you can use optimization, but not necessarily where you would want to use it. Because really using it would mean needing some science behind us. And right now we're in math and don't have the same science knowledge. So it's an attempt to give a problem that is, you know, I don't know what I'm saying.